Section 3.7 is all about motion. These are the infamous distance, rate, and time when train leaves the station and goes the opposite directions. Like, these are like everything you hear about in algebra word problems. Here you go. A jet leaves the O'Hare Airport in Chicago at 7 a.m. and flies south towards Atlanta, 606 air miles away at an average speed of 420 miles per hour. At the same time, a jet leaves Atlanta and flies towards Chicago at an average rate of 500 miles per hour. Because of an error in calculations, the jet are flying at the same altitude and on the same route towards each other. This is a problem, by the way. How much time do the air traffic controllers have to change the direction or altitude of the jets before they collide? So they're going two different speeds. They are heading towards each other, and they are 606 miles apart. And so you would use distance, rate, and time to figure out how long it would be before they would meet inadvertently in the air, which is not good for planes to do. All right? And so this is a type of uniform problem. This is a type of uniform motion problem. All right? We're going to start out with basic distance, rate, and time. So the distance you travel is equal to how fast you are going times how long you are going that fast. The formula here is distance equals your rate multiplied by your time, okay? You are going to use this over and over and over in this section. Distance equals rate times time. So the example they give you here, if you are going 50 miles an hour for 3 hours, you will travel 150 miles. All right? How far can a car travel if it goes 50 miles an hour for t hours or time hours? 50 times t. And then they give another example. At what rate is the car traveling if it goes 225 miles in 5 hours? You see, they use the same thing, except they gave us the distance. Distance equals rate times time. So in this case, to solve, I'm going to divide. All right, just like the problems we've been doing. You're going to be given things. You're going to set it up for distance, rate, and time, and then you're going to solve for whatever you're missing in that piece. All right? And so it says, if you ride your bike 12 miles an hour, how long would it take you to travel 72 miles? So let's look and see, what did they give us? 12 miles per hour. Is that distance, rate, or time? 12 miles per hour. Is that distance, rate, or time? Rate. All right, the next thing they gave us is 72 miles. Did they give us distance, rate, or time? Distance. And then you'll notice the words, how long? What are you looking for? So what you don't know here is time. So we are going to use the formula right here. Distance equals rate times time. So we will set this problem up just like that. Distance equals rate times the time. How do I solve for this one? Divide. So what is 72 divided by 12? Yeah, so my time equals 6. It is miles per what? Hour. So 6 hours. Pay attention to your units, because sometimes they'll say this many minutes and you need to convert it to hours, or vice versa. You need to convert your travel time to minutes because you don't want to use two different units. So pay attention to your units. All right. So look at the next question. If you swim 130 yards in 1 minute, how many yards would you swim in 25 minutes? What did they give us? They said you swim 130 yards per minute. What is that? Distance, rate, or time?
Distance.
It's distance compared to time, so it's rate, okay? So they actually gave us the rate here, 130 yards per minute, all right? And then the next one they said was 25 minutes. What did they give us there? Distance, rate, or time? Time. And then the next question here, the question they're actually asking, how many yards? Distance, rate, or time? Distance. All right. So we're going to set this up. Distance equals rate, 130, times time, 25. What do I do to solve? Multiply. So what happens when you multiply 25 times 130? 30. 3,250 what? Yards. All right. So go ahead and try 3, 4, and 5 there. 18 miles in 8 hours. How fast are you going in miles per hour? All right. So they gave you the distance, right? You walked 18 miles. And they gave you the time, 8 hours. They did not give you the rate. So how are you going to solve for the rate? Divide. You're going to say 18 divided by 8. And you should have gotten around 2 1/4. So 2.25 miles per hour. 2.25 miles per hour. All right, let's look at the next one. A car traveling 55 miles per hour for 3.5 hours. How far has it traveled? What did they give you? Distance, rate, time. What 2 did they give you?
Rate and time.
Rate and time. So distance equals rate times your time. What did you need to do here to solve for this one?
Multiply.
Just multiply. So you would have gone 192.5 miles. 192.5 miles. All right. And then let's look at the last one. It says 2 cars leave town at the same time. The first car travels 315 miles in 3 hours. The second car travels 95 miles in 1 1/4 hours. Which car travels faster? So for the first car, we're going to have to do 2 separate equations here. For the first car, they gave us what? Distance, right? 315. And they gave us time. So distance equals rate times time. So you should have divided by 3 there, and you would have gotten 105 miles per hour. That is really fast, right? For the second car, they drove, distance is 95. The time is 1.25 or 1 1/4, however you do it, times your rate. Again, you would have divided and you would have gotten 76 miles per hour. Which car is going faster? Well, the first car. All right. Towards each other. All right, so when you start getting a word problem, the first thing you would do is you want to read through it and see what type of problem do I have, all right? With opposite direction and when they're walking towards each other, the distances will not necessarily be the same, all right? And so for an opposite direction problem, they'll say, oh, well, the first car left this point and traveled east, and the second car left the same point and traveled west. And then after a certain period of time, they were, in this case, 1,000 miles apart. So this guy's distance and that guy's distance should equal 1,000 miles apart. Now you can see they're not necessarily the same. Maybe this guy was going faster than this guy, or maybe one left earlier or whatever. But some different situation caused them to have different distances. But if you add their 2 distances up, it should equal the total distance apart. So if I were to take 2 of you and set you in the middle of the room and say start walking in opposite directions and then just say stop, what each person's distance added together should be how far apart you are. And that's what opposite direction does. The same concept is true as when you're traveling towards each other, all right? You leave different spots, you're traveling towards each other, and you meet. Once again, y'all may be traveling at different rates, but by the time you meet, if you add your 2 distances together, it should equal the total distance you were apart when you started. Okay? So these problems, when you're going opposite direction or when you're heading towards each other, you're going to set up a distance, rate, and time for each individual piece of it. And then you're going to add them up, and that should equal the total distance apart. So opposite direction and towards each other, that's the first type of problem we're going to do. This is our first type of problem, opposite direction or towards each other. You'll notice that there's a chart set up. This is how I would recommend you solve these. And so for the handout, most of these have charts. If you get a word problem from me, I'm not going to provide you with a chart. So you're going to want to create a chart like this for the two vehicles or people or whatever's traveling. You want to set up a chart for each of them. It says Judy and David each go on separate trips in opposite directions. So that is the key word we're looking for here, opposite direction. That tells us that each of their distances is going to be added up to calculate distance apart. David drives twice as fast as Judy. David travels for 3 hours while Judy travels for 2. They drive a total of 324 miles. How fast and how far do Judy and David drive? So the first thing they ask us is, what type of problem is this? Well, they told us what type of problem. This is an opposite direction. So this is an opposite direction type of problem. All right. Well, what do we know about opposite direction problems? We know that the two distances, distance 1 plus distance 2, should equal the total distance apart. All right. So let's see what we know. We're going to pick out what we know first, okay? We know a couple things absolutely for sure. David travels for 3 hours. So they gave us information about David. Specifically, did they give us David's distance, his rate, or his time? His time. So David's time is going to be 3. David's time is going to be 3. All right. Judy travels for 2 hours. They gave us information about Judy. What did they give us about Judy? Her distance, rate, or time? They gave us her time. She is traveling for 2 hours. All right. Then they gave us a relationship between something. They said David travels twice as fast as Judy. Did they tell us how fast Judy is going? They did not. So if I don't know how fast she's going, what do I put there when I don't know something? An X or a variable. In this case, you can use R, D, and T if you want to. If you do, I'm going to recommend that you are very, very clear about your T's. This is just advice here. What's the problem if I write a T like this? Looks like a plus sign, okay? So be very intentional about what you're writing. I do recommend you use D, R, and T, because then at the end, when you get a weird number, like for example, I've used the example, if you get that you're traveling in a boat at 700 miles an hour, that's not a valid rate for a boat, right? Because you will be airborne in a boat at 700 miles an hour. And so it's very important that at the end you remember what you were solving for, all right? So it's very important that at the end you know what you were solving for. And so using D, R, and T reminds you I'm finding distance, or I'm finding rate, or I'm finding time. But if you do, be very, very clear about your T's. Make a little hook at the end. Make sure you know it is not a plus sign, okay? But anyway, we do not know her rate, so we are going to put a variable there. You can put R, you can put X, but we do not know her rate. They told us David travels twice as fast as Judy. If Judy is going R miles an hour, how fast is David going? 2R, yes, 2R. So David's rate is 2R. Okay? So far, so good. I have rate and I have time. How do I solve for distance when I have rate and I have time? What do I do to those to find distance? You multiply. So I'm literally going to multiply this group here. R times 2. We would write that to R. 2R times 3. What is that? 6R. And so I have my entire chart filled out. Now I set up here the two distances which I just found right here, should add up and equal the total distance apart. So do I know the total distance apart? Yes. They drive a total of 324 miles. So I am now going to take this equation here that I have, and I'm going to say 2r, Judy's distance, plus 6r, David's distance, should equal the total distance apart, 324. 2r plus 6r should equal 324. Can I solve this equation now? Yes. How do I solve it? Right. Combine my like terms. 2r and 6r gives me how many r's? 8r equals 324. How do I solve for r then? Divide. Divide by 8. What is 324 divided by 8? R equals 40.5. What did I just solve for? Distance, rate, or time? Specifically, whose rate was R? Judy. So how fast did Judy drive? I just solved that. She drove 40.5 miles per hour. All right. How then do I solve for David's? Multiply by 2. What happens when I multiply by 2? 81 miles per hour. How far did David drive? How do I find that? How do I find David's distance? I have his rate. I just solved for this. I know his time. How do I find his distance? You multiply his rate by his time. So we're going to take the 81 and we're going to multiply it by the 2 hours that he drove. So how far, 3 hours that he drove. David is 3. So how far did he drive? 243 miles. We're going to do the same thing for Judy. She drove 40.5 miles per hour for 2 hours. How far did she drive? 81 miles. Two best friends live 300 miles apart. They decide to meet one day for lunch. This is the same concept, except they're leaving and meeting. They agree to leave their homes at the same time and drive toward each other and meet somewhere along the way. One friend drives very carefully and obeys the speed limit, her average, and they give it there. The other drives too fast. They give her average. How long will it take for them to meet? How far did they drive? What type of problem is this? This is a problem where they are traveling toward each other. The same as before, the first distance plus the second distance should equal the total distance here. All right? It says, one friend drives carefully and obeys the speed limit. Her average speed is 65 miles an hour. So we know the rate of the first friend here, 65 miles an hour. The second friend drives fast. Her average speed is 80 miles an hour. All right. Do we know the time? We just know that they're going to meet on the way. So wherever they meet is where they're going to stop. They left at the same time. They're going to obviously meet at the same time. So their time should be the same, but we don't know what it is. So what are we going to put there? We're going to put a variable, right? A variable. So then to calculate the distance, we just multiply the rate times the time. The first friend's distance was 65 times t. The second friend's distance was 80 times t. Because we know what type of problem this is, we are going to add their distances. 65t plus 80t should equal their total distance apart. How far apart were they? 300. All right. You should have gotten, by the way, their time. Their time is 2.1 hours, which is 2 hours and 6 minutes. You should have gotten that The first friend, when you multiply, drove 136.5 miles. The second one drove 168 miles. Approximately 11 o'clock, if you want to be exact, 10:54. But approximately 11 o'clock is when they would have left their house. So the next type of motion problem is round trip. For round trip, you leave one spot, you travel, and then you travel back. And so what should be true of these distances? If you leave and go to a point and then leave that point and come back, what should be true of these distances? Well, they should be the same, okay? And typically they will say they took the same route. So they remove any other variables, like maybe you went home a different way, okay? So for this type of equation, you're not going to add the distances up. You are going to set them equal to each other, all right? And so they'll give you a scenario. You will do the same type of chart. You will calculate the distance based on your chart, and then you will set them equal to each other, and then you will solve. So let's look at the one on your handout, okay? So this is the first example of round trip. All right. So it's asking us what type of uniform problem is this? And this is a round trip. This is a round trip, meaning we go there and we come back. What do I know about this type of problem? Well, I know that the distances should be equal. So the first distance, or the distance there, should be equal to the distance back, or the second distance. This says a cargo plane flew to Hawaii and back. Flew to Hawaii and back. That is a round trip, there and back. It took 20 minutes less time to get there than it did to get back. The average speed of the trip there was 300 miles an hour. The average speed on the way back was 280 miles per hour. How many hours did the trip there take? How long did it take to return? How far was it to Hawaii? So they've asked several questions here. We need to fill out the chart first and see what we're missing. All right. So the first thing we're going to look at then is they have given us speed. They've given us two different speeds, two different rates, 300 miles an hour, 280 miles an hour. When you do a round trip, you want to set it up with there and back. There and back. That's how your round trip charts will look. So what was the rate on the way there? 300. So I'm going to write 300. What was the rate on the way back? 280. Do I know either time? I do not. They said it took 20 minutes less time to get there. That makes sense. They were going faster, right? However, they gave it to me in miles per hour, not minutes, okay? So they have compared the way there compared to the way back, all right? So I'm going to write my variable in the way back, okay? And then if I want to say less time, am I going to add or subtract time? I'm going to subtract. It was not 20 hours, it was 20 minutes. So I need to write that in terms of hours. How many minutes are in an hour? So I have 20 out of 60 minutes. So it is 1/3. Does everybody see that? It's going to be 1/3, all right? So I'm going to say my rate going back minus 1/3 of an hour. 20 minutes is 1/3 of an hour. You will not want to use a decimal here. Why do you think I would not want you to use a decimal here? So I have the basics of my chart set up. Just like every other chart, my rate multiplied by my time equals my distance. So then what is the distance of the way to Hawaii? Well, I'm going to say my rate, 300, times my time, r minus 1/3. My distance on the way back is my rate multiplied by my time. That is going to be 280 times r. So my chart is completely filled out. How do I solve? Well, I go right back up here to say, what do I know about these distances? I know that they are the same. So that's what I'm going to do. I'm going to take these distances and I'm going to set them equal to each other. I'm going to say 300 times r minus 1/3 equals 280 times r. And they were nice with that fraction because it's going to completely go away when we distribute. So all I have to do is solve this equation. Distribute your 300. 300 times r. 300 times negative 1/3. All right, what is that? Yeah, just negative 100. You divide by that 3 and multiply by the negative 1. So negative 100 equals 280 times r. What do I do now?
You have to put the variable on one side.
Variables on one side, numbers on the other. Since I already have a variable by itself over here, move your variables over, okay? If not, you're going to put them on the same side and you're going to mess up. So if you already have a variable somewhat by itself over here, move the other one over. So minus 300 So I'm going to get negative 100 equals 280 minus 300 is what? Negative 20r. All right. My final step here is to divide by negative 20. 100 divided by negative 20 is just 5. What did I solve for?
Back.
Specifically, what did I solve for?
Time.
Time and on the way back, right? So I solved for, actually not, yeah, I solved for, and I put an R, I should have put a T there. I solved for my time on the way back, all right? My time on the way back. So which question did I answer down here? Which question? How long did it get away? How long to return? What was the distance? How long was the return flight? That was 5 hours, right? That was 5 hours. How long then did it take to get there? Well, 20 minutes less. So how long did it take? 4 hours and how many minutes? There we go. 4 hours and 40 minutes. 4 hours and 40 minutes. I just subtracted 20 minutes. What is the distance to Hawaii? Well, the distances are the same. So you can multiply the 4 hours and 40 minutes times the rate. I personally wouldn't do that particular one. Or you can multiply the 5 hours times the rate. I would actually do that one. That's going to be a little bit easier. So you can say, well, if the rates are the same, if the time's the same, I can just plug this in. 280 miles per hour times 5 hours is going to give me 1,400. So the total distance was 1,400 miles. I'm going to change all of these guys to T's because it's going to throw everybody off. really quickly. It's a round trip, so we know the distances equal each other. They told us that on the way up the mountain, he went 3.5 or 3.5 miles per hour. On the way down, he went 4.8 miles per hour. We do not know the time of either. We know the total time was 5. So if I put a time here as a variable, then 5 minus that is the leftover time. So that would be how long it took him on the way down. I just multiply across to get this column. 3.5 times t, 4.8. Remember, you group it. If you have a plus or minus, must put parentheses around it. These are equal, so I set them equal to each other. I distributed here. 4.8 times 5, 4.8 times negative t. Moved my variable over by adding. I got 8.3 equals 24. When you divide, you get 2.9. Little note here, you would not say it took me 2.9 hours. That is strange to say it that way, right? You usually do the hours and minutes. So the hours is the whole number, the 2. 0.9 of an hour is just 0.9 times 60 minutes. 0.9 times 60 minutes is 54 minutes, all right? So 2 hours and 54 minutes. If you subtract that from 5, you have left over 2 hours and 6 minutes. So on the way up the mountain, it took 2 hours and 54 minutes. On the way down, 2 hours and 6 minutes. Look and make sure this is logical. He went slower on the way up, which one likely would, than he did on the way down. So it would make sense that the slower he went, the longer it would take. The faster he went, the shorter it would take. You can logically see if at least your answers are lining up with logic. All right? To then calculate how far it was, you could plug it into either one. But once again, the easiest one to plug it into is this guy. So I just did, and you'll notice I left it as a decimal here because I'm multiplying. I'm not going to multiply hours and minutes. I'm going to multiply in decimal form. So I did his rate multiplied by his time in decimal form. 10.15 miles is what we get there. So in these types of problems, someone leaves, and then however much time later, someone else leaves. And typically the one that leaves later is going faster because they want to know how long it takes for them to catch up or for them to be at the same point. All right? However, they leave at the same point. They catch up at each other at the same point. So once again, these distances are the same. These distances are the same. They're typically called like catch-up problems, all right? So here it says head start, whichever way you want to write it. But typically one leaves and another one leaves later, and then they catch up at some point. And so the example here, Trey and Justin left for a trip down a river in a canoe, maintaining a constant speed of 3.7 miles per hour. 3 hours later, Trey's father set out after them in a motorboat carrying camping supplies. The motorboat traveled at 16 miles an hour. How long after he started did Trey's father catch up with the boys? How far had they traveled? How long had they been on the river? All right. This is a same direction problem. This is a same direction problem. So same direction is what we call it normally. It can either be head start, where they got a head start, where they caught up. But this is same direction. They left at the same point. They caught up with each other at the same point. All right. So this type of problem is the same direction. We're not going round trip. We're not going opposite directions. We are going the same direction. One is just leaving at a different time and traveling at a different rate. I do know, however, that these, just like my round trip, my distances will equal each other. So what have they told me? They've told me that the boys were traveling at 3.7 miles per hour. So Trey and Justin is my first row here, and the rate for them is 3.7. They also told me that Trey's dad was traveling at a rate of 16 miles per hour. So that is the rate for Trey's father. Do I know either of their times? I do not, all right? So I know then that Trey and Justin left at some time. I just don't know what. If their dad left 3 hours later, did he travel for more time or less time? less time, right? He was going faster. And I'll tell you, if you just figure out which one's going faster, they're going to be the ones traveling less time in these, okay? So that means I'm going to take Trey and Justin's time and I'm going to add or subtract the 3 hours. Yeah, so I'm going to subtract 3 hours from their time to get their dad's time, or to get Trey's dad's time. And then as always, you just multiply across to get the distance. 3.7 times t, 16, don't forget to group the t minus 3. For same direction where they're catching up with each other, those distances equal each other. So that's exactly what I'm going to do. 3.7t equals 16t minus 3. All right, now you're just going to solve, distribute and solve. So I am going to take the 16, I'm going to distribute it through. I'm going to subtract my 16t over. Remember to line up your decimals. You are using calculators to make sure you put your decimals in correctly. 3.7 minus my 16 is going to be negative 12.3. And don't forget to bring this negative down with the 48, negative 48. Then my final step here is to divide by the negative 12.3. So your time is approximately 3.9. And it's okay to round your time to the nearest one decimal place, because if you get to like multiple decimal places for time, it's going to be weird when you multiply it for your minutes. What did we just solve for? Which time for whom?
We solved for
Trey and Justin. So once again, I'm going to take that 3, and that is my hours. My 0.9 times my 60 minute is going to be 54 minutes. So how long had the boys been on the river is what we just solved for. That is the time. 3 hours and 54 minutes. 3 hours and 54 minutes. All right. The dad traveled how much less time? 3 hours. So how long had he traveled? How long? He traveled 54 minutes. We're answering this question right here. How far had the boys traveled? Well, to find distance, we take their rate, which was 3.7, multiplied by their time, 3.9. So you should get 14.43 there for their distance, 14.43 miles.